So a composite beam is made by casting 300 into 900 mm precast prestressed with cast in situ slab of 1500 into 150 mm. Okay, so here a composite beam is made by casting 300 mm into 900 mm precast prestressed with a cast in situ slab of 1500 into 150 mm. Okay, so the composite beam consists of one beam, one slab. Okay, the beam size is 300 mm into 900 mm and the slab size is 1500 into 150 mm. Okay, so the effective pre-stress of 12 MPa at the soffit. Okay, so the effective pre-stress that stress is 12 MPa at the soffit. What is the soffit? Soffit means bottom of the beam. So at bottom stress, in case of effective pre-stress, it is 12 MPa and 0 at the top. Okay, so it is 0 at the top. Calculate the UDL load. Calculate the UDL load for the composite action on a simply supported span of 16 meter. Okay, so we have to calculate the UDL load for the composite action on a simply supported span. So here they given span. Okay, so the condition is in unpropped condition and propped construction. So concrete weight is density or otherwise called density is 25 kilonewton per meter cube. So in this given problem, they given the stress and what they asking what is the live load, that means external load. Okay, students. So first we need to calculate self height of the beam. What is the self height of the beam? So first we have to focus unpropped condition, after that propped condition. So in this unpropped condition, first we need to calculate self height of the beam. So what is the beam size? You can see here 300 mm into 900 mm. So 0.3 into 0.9 into 25. 25 is the density of the concrete. It is also given in the question. So we got 6.75 kilonewton per meter. This is the self height of the beam. Next, bending moment due to precast beam. 6.75 into 16 square divided by 8. What is the simply supported beam carries UDL load means? What is the bending moment, maximum bending moment formula? It is WL square by 8. Okay, so it is 216 kilonewton meter. Okay, so coming to second moment of area, that means BD cube by 12. So 1.82 into 10 power 10 mm power 4. That means 300 into 900 cube divided by 12. Okay. Next, flexural stress due to precast beam. So stress due to the self height of the beam. So it is M by Z. So here you can see M. Okay, and this is your Z value. Okay. BD square by 6. What is the Z value? BD square by 6. Actually, this is I value, not Z value. It is I value. Z value for rectangular section is Z formula. What is the Z formula? It is BD square by 6. So B is 300, D is 900 square divided by 6. So what is the stress due to self height? It is 5.33 Newton per mm square. Okay. So now the beam part is over. Next, coming to slab part. So what is the size of the slab? 1.5. That means 1500 mm into 150 mm. That means 1.5 meter into 0.15 meter. Okay, so 1.5 meter into 0.15 meter into 25. 25 is the density of the concrete. So therefore, the self height of the in situ slab is 5.63 kilonewton per meter. Okay, 5.63 kilonewton per meter. Next, coming to bending moment. So same formula, WL square by 8. So 5.63 into L square, 16 square by 8, we got 180.2 kilonewton meter. Okay. Next, corresponding section modulus, BD square by 6. Okay, BD square by 6 we already found. Here you can see BD square by 6. So this is unpropped condition. Sir, here you may wonder, sir, why, sir, you didn't calculate that for slab BD square by 6. So slab B for unpropped condition, the slab weight is transferred to the beam only. So we have to put beam section modulus, not a slab. Okay. So here you can see BD square by 6. So corresponding M. So this M is nothing but self-height moment due to slab. Okay, students, here only you have while writing in examination, you may have doubt. Okay, so in case of cast institute slab, we have to find stress, means we have to put bending moment due to self height of the slab divided by Z value is the beam section modulus. That means Z value is beam section modulus only we have to put, because the stress is transferred to the beam only. So from this, stress is 4.45 Newton per mm square. Okay, Newton per mm square. So this bending moment live load is WL square by 8, and W into 60 square by 8 is called 32 W kilonewton meter. So this moment, that means the live load is taken care by both slab and beam. Okay, both slab and beam. So this bending moment due to live load is 32 W kilonewton meter is taken care by both slab and beam. So here we need to consider as composite section. Okay, here only we have to consider the composite action is occurs. So we need to calculate the YT and YB. That means centroid distance at top and centroid distance at bottom and IXX value. So that is our next step. So you can see, taking this soffit of the beam as reference. That means bottom of the beam as reference. So Y bar is equal to, what is the Y bar formula, centroid formula? A1 Y1 plus A2 Y2 divided by A1 plus A2. Okay. So therefore Y bar is equal to 300 into, what is the area of the beam? 300 into 900. So centroid is 900 by 2, 450. Next, coming to slab, area of the slab, 1500 into 150, and the centroid distance from the bottom of the beam to the center of the slab is 975. Okay, so that means you can see here, that means from center to this side, it is 975. 975. Okay. So next, coming to A1 plus A2. So the area of first cross section beam is 300 into 900. Area of that rectangular portion of the slab is 1500 into 150. Next, Y bar equal to 688.6 mm. Next, coming to IXX. So we know that IXX formula. So this are already we seen. Okay, how to calculate IS BDQ by 12. So each portion you calculate BDQ by 12. Okay, so that is your IXX. And coming to ZT and ZB, that means section modulus at top and section modulus at bottom. So IXX divided by YT and ZB is equal to IXX divided by YP. So IXX divided by YT is how much? So we know the IXX value. What is that IXX value? 5.68 into 10 power 10. What is YT value? YT is nothing but overall depth minus this Y bar. Actually, this is YB. Okay, so that is your YT. So next, coming to ZB, IXX divided by, that means 5.68 into 10 power 10 divided by, this is YB. Actually, we taken centered from the bottom only, so it is YB. So 688.6 mm. So from this we calculated ZT, that means section modulus at top and section modulus at bottom. Okay. So next, coming to stress due to live load at the soffit of the beam. So what is the stress due to live load? So M by Z. M by Z. So what is the moment value due to live load? It is 32 W into 10 power 6. This is the moment value due to live load. divided by Z. That means section modulus is 82.5 into 10 power 6. Okay, this is your Z value. Okay, so from this draw the diagram. So you can see this is the T section and this is your effective stress. This is given in the question. 12 Newton per mm square at bottom and 0 stress at top. Next diagram, stress due to self weight of the beam, 5.33 Newton per mm square. Next is stress due to self weight of the slab, 4.45 Newton per mm square. Okay, so next stress due to live load. You can see the fourth diagram is stress due to live load. So what is the stress due to live load at bottom? It is 0.4 W. So now the resultant stress is 0. So we have to equate the resultant stress is 0. Okay, so there is no tensile stress. So resultant stress is 0. So you add all the values, bottom values, which is equal to 0. That means 12 minus 5.33 minus 4.45 minus 0.42 W. 42 W or 0.44? Okay, 0.42 W. Here they mentioned wrongly. It is 0.42 W. Okay, so 12, you can see 12 is plus value. And this 5.33. So we know that self weight due to beam and self weight due to the slab only acting means the tension goes bottom, compression goes top. Okay, so that we put minus. So 12 minus 5.33 minus 4.45 minus 4W equal to 0. So therefore W, that means live load. Live load is 5.29 kilonewton per meter. This is your live load. Okay. Next, coming to load intensity per kilonewton per meter square. So here, this is the question they asked. What is the load intensity means? Actually, this is not required, but they found load intensity means we have to multiply by this 1.5 meter. That means you can see the slab goes like this. Okay, goes like this. So for the 1 meter, length, okay, for the 1 meter length, this hatched portion, how much load is acting? That means in terms of kilonewton per meter square. In terms of kilonewton per meter square. So we can see here 5.29 divided by 1.5. So if you put divided by 1.5 means we got 3.53 kilonewton per meter square. This is the answer. So this is for the propped condition. Okay, this is as per propped condition. Sorry, it is not propped, it is unpropped condition. Okay, this diagram is for unpropped condition. So far we discussed for unpropped condition. Next we will see propped condition. Okay, so any doubt means now you can ask me, students. So in case of coming to second part, it is propped construction. So in case of propped construction, only one thing is different. That means the stress due to this portion. Okay, only different. Due to the self weight of the slab is taking whole the portion. So here you can see what is the bending moment. In cast in situ slab bending moment, we already calculated 180.2. 180.2. So now divided by ZB. ZB is we have to put the we have to consider the whole section. That means including slab and beam composite action. So that ZB is nothing but 82.5 into 10 power 6. Okay, 82.5 10 power 6. So therefore bending moment due to cast in situ slab 180.2 into 10 power 6 divided by 82.5 into 10 power 6. So we got 2.18 Newton per mm square. Okay, so we got 2.18 Newton per mm square. So this is the stress due to cast in situ slab, 2.18. So now you can see, students, based on this, draw the diagram. So up to this at level. So this is stress due to self height of the slab. Okay, so see the difference between previous diagram and this diagram. Okay, in previous diagram, that means unpropped condition, so we drawn up to the bottom of the slab, because the stress due to self height is taken care by the beam. Okay, so now the stress due to self height of the slab is taken care by the whole section. Okay, that is the major difference. So the value is 2.18. Okay, so other things are same. So you can add all those things value, you can get the answer. So 12 minus 5.33 minus 2.18 minus 0.4 W. So therefore W is kilonewton per meter. Actually it is wrong, it is not meter square. So 11.22 kilonewton per meter. 11.22 kilonewton per meter. So the live load intensity is 11.22 divided by the length of the breadth of the T section. That means breadth of the slab 1500. So 1.5 meter. So 11.22 divided by 1.5, which is equal to 7.48 kilonewton per meter square. Okay, students. So this is your another important problem. So if we study these two problems in composite section, means it is enough. You can easily get full mark. The only thing is you have to know the difference between propped construction and unpropped construction, and how to draw the stress distribution diagram. Okay, so once you know this, means you can easily solve this type of problem. Okay, students. So now go through this problem, students, once again. If you have any doubt, means ask me now. So don't waste this time. Utilize this time for clarification. If you have any clarification. So here I am discussing only exam point of view problems only. Okay, so these are all most important problems under exam point of view. Okay. So go through, students. If you have any doubt, means ask me now. So today we will discuss what is meant by differential shrinkage, what is the effect. So next class we will discuss problem. Okay, students. So differential shrinkage in composite beams. So we know that the precast pre-stressed beams are casted already and it's placed. In above that, the fresh concrete is placed. So the property of the material of the both concrete is different. Okay, so that pre-stressed members already casted cured. Okay, but in case of fresh concrete, it is not casted before. So on the place only, that means above the beam only it is casted. Okay, a casted and cured. Okay, so the property of the shrinkage creep is difference between already casted beam, pre-stressed beam, and newly casted in situ slab. So due to this, the differential shrinkage stress is developed. Differential shrinkage stress is developed in the beam. So this portion is discussed that only. So this is the outline of the topic. Okay, so you can see here in composite construction, the precast pre-stressed beams are resisting the applied loads along with the cast in situ slab. As the precast elements were placed much earlier, creep and shrinkage would have already taken place. Okay, the bed concrete of slab is laid over the precast unit. That means wet concrete means fresh concrete. Okay, so now only it is prepared. It is in not a hardened state, it is in fresh state. So the wet concrete of slab is laid over the precast unit. Okay, laid over the precast unit, and the shrinkage and creep continues. So there will be a difference in shrinkage and creep in the precast unit as well as in the slab. The stresses are computed as follows. Let shrinkage strain and EC means X modulus of concrete, and AA be the shrinkage strain, modulus of elasticity of in situ concrete, and the cross-sectional area of the in situ slab. Okay, so here epsilon CS is nothing but shrinkage strain. They mentioned here shrinkage strain, and EC is modulus of elasticity, and A is nothing but cross-sectional area of the in situ slab. The magnitude of the tensile force, okay, the magnitude of the tensile force NSH is computed from the following equation. So NSH equal to, that means force due to this creep and shrinkage. So there will be tensile forces developed. So how to calculate the tensile force? So it is shrinkage strain multiplied by Young's modulus of concrete multiplied by area of in situ slabs. So if you multiply by all those things, we can get the tensile force. So this tensile force is balanced by a compressive force applied at the centroid of equal magnitude. Okay, the force applied at the cast in situ slab causes a direct force acting at the centroid of the composite section to gather the bending moment. So here we are applying automatically due to the shrinkage strain, there will be a tensile force is developed. Okay, and it is balanced by a compressive force. So in which form we are applying compressive force? Due to the pre-tensioning wires. Okay, so at the centroid of the equal magnitude, the force applied at the cast in situ slab causes a direct force. Due to this force, there will be a direct force is developed acting at the centroid of the composite section together with a bending moment. Okay, so definitely if force is there, means there will be a bending moment also is there. Okay, so next, this creates a direct force and a bending moment causes direct and bending stresses. Okay, due to this force, there will be a direct and bending stress will develop. The estimation of shrinkage stress can be explained briefly as follows. If the top of the cast in situ slab has restrained against contraction, a uniform tensile stress would develop due to differential shrinkage. Okay, so yeah, restrained construction is occurred means a uniform tensile stress is developed. Tensile stress means what? It's a negative stress. Okay, so we have to avoid the tensile stress in the prestressed construction. Okay, so that negative stress, tensile stress is developed due to this differential shrinkage. Okay, next, this imaginary restrained force acts at the mid depth of the slab. This imaginary restrained force acts at the mid depth of the slab. Okay, as in self-equilibrating system, equilibrating nothing but equilibrium. Okay, under equilibrium condition, a balancing compressive force will act in the composite action. Okay, this results in a compressive force and a moment in the composite action. Okay. Next, fourth one, the axial and bending stress can be calculated for the above effects and added to the uniform tensile stresses to obtain the stress due to differential shrinkage. So how to find stress due to shrinkage? Differential shrinkage means the axial and bending stress can be calculated. First, we need to calculate axial and bending stress for the above effects and added to the uniform tensile stress. So finally, we have to add the uniform tensile stress. Okay, the formula to compute the stress due to differential shrinkage are as follows. You can see here, see the diagram, students. Here there will be a small I section, precast beam is there, and above that a cast in situ slab is there. Okay, so this is the top of the slab, bottom of the slab, and the cast in situ slab, and the composite centroid, composite action centroid, and the precast centroid, bottom of the beam. So under this condition, stress at the top fiber of the slab, stress at the top fiber, that means here at top, equal to PS divided by AC plus M divided by ZT minus F. Next, coming to stress at the bottom fiber of the slab. Bottom fiber is nothing but at junction. It is PS divided by AC plus M divided by ZB minus F. Next, coming to stress at the top fiber of the beam. Okay, that means here stress at the top fiber of the beam. PS divided by AC plus M divided by SJ. SJ is nothing, ZJ. ZJ is nothing but junction. Okay. Next, stress at the bottom fiber of the beam. PS divided by AC minus M divided by ZB. Okay. So F is nothing but uniform tensile stress at the center of the slab. Uniform tensile stress at center of the slab. Next, PS and M are the direct compressive force and the bending moment. Okay, PS is nothing but direct compressive force and bending moment. Next, AC is equal to area of composite section. AC is nothing but area of total area of the composite section. And ZT and ZJ and ZB, which is equal to section moduli at top, section moduli at junction, and section moduli at bottom of the precast beam respectively. Okay, so these are all the formulas we have to use in the shrinkage stress formula. Okay, students. So tomorrow we will see 2 more problems. Okay, not tomorrow, day after tomorrow. Okay, so Wednesday we have 2 classes. In the 2 classes we will finish our